Welcome to the panel discussion all about informatics and design. My name is Alyssa Walker. I will be your moderator for this session today. And as with Paul, I hope you all enjoyed the chance to check out the student posters and the research that they represent. We also have a fantastic group of researchers and thought leaders comprising our panel today. And I will introduce them here in just a moment, but first wanted to just share a couple of quick reminders. This will be, a panel discussion, but we want it to be interactive as well, of course. So as with the previous sessions, please, if you have questions, feel free to post those in the chat and we will be monitoring those. And particularly during the second half of the discussion, we will do our best to integrate those into the session and the conversation. And then just another reminder, I know Paul mentioned this earlier as well, but I know this session starts to push into the lunch hour for some of you. The great thing about a virtual event, of course, is that you don't have to walk away while you grab your lunch. You can keep those headphones in and stay with us because you won't want to miss this discussion, I can assure you. So those reminders out of the way, let me introduce our panelists. I'm very excited for this group today. I was able to meet with them recently in preparation for today's session and got a little bit of a sneak peek, if you will, of some of the things that they will be sharing and discussing, and just their energy overall for the topic. So I'm very excited for you to have the opportunity to hear from John, Tucker, and Jessica, and let me just provided some quick background for each of them for you before we dive into our conversation. So we'll start with John Hiller. Dr. John Hiller is an industry expert in generative design. With a PhD in mechanical engineering, he served as the founding CTO of Frustum until it was acquired by PTC, where he worked in the office of the CTO to further Frustum's generative design vision within the PTC product portfolio through advanced research. His work today continues to focus on driving the shift from traditional CAD to functional generative design. So very fortunate to have John here today with us. Thanks, John, for being here. Next, we have Dr. Tucker Marion, who's joining us from Northeastern University here in Boston. Tucker is a jointly appointed associate professor in the DeMaury McKim School of Business and the Mechanical and Industrial Engineering Department of the College of Engineering. He is the Director of Partnership Innovation, as well as the Faculty Director of the Masters in Management and Innovation programs. So just a few things going on there, right, Tucker? His interdisciplinary research is centered on the new product development and design process. And specifically, he researches critical attributes that can influence the efficiency and efficacy of the process, which include implementing startup approaches to design, information technology, and digital design integration and usage, and the effect of outside design resources. So great to have you here, Tucker, and we'll look forward to hearing some of your thoughts today. And then last, but of course not least, we have Dr. Jessica Menold joining us from Penn State University. Jessica is Associate Professor in Engineering Design and Mechanical Engineering at in the Technology and Human Research and Engineering Design, or THREAD group. She leads that, and her work there focuses largely on exploring the interplay between people, products, and processes in an effort to improve design practice. Jessica is also the director of the Center for Immersive Experiences, which seeks to create leadership in immersive experiences by advancing the underlying science of those technologies and integrating them into the academic spectrum through research, education, and outreach. So a very knowledgeable, experienced group here with us today for today's discussion. Again, very happy to have all three of you here with us and looking forward to your thoughts and insights. So with that, we'll get started. So the title of today's panel discussion is Informatics and Design. And when we say that, for the purposes of our discussion today, we're really talking about how the data made available through cloud technologies can change engineering design and product development. Our hope as a panel is that you as our audience will walk away with a better understanding of the ways that cloud native engineering technologies are enabling advanced research. So let's jump in. And Tucker, we'll start with you, where your work encompasses the earliest stages of the product development process and product ideation. I think that's a natural place to begin. So I've got a two-part question for you. First, how can informatics be used to help conceptualize new products? And then the second part of the question is, why is it important for teams to use data to make design decisions early on in their development process?
All right, well, great question. And maybe I'll start with the second part first, is that the upfront of the development process, we know from research and practice, is arguably the most important, because that's where your architecture is decided. It's where customer needs are translated into functional specifications. The bulk of the ultimate cost structure of a product is determined very upfront. So the more that we can use data to inform that process, the better. And I like to think of it that there's two parts of data. There's data from the outside, but there's also data from the inside that can be very valuable to improving the process. So on the first part of the question, companies, unfortunately, even today, don't use as much as the data that's afforded out in the world as they could, from customer reviews to data that's gathered from IoT solutions, for example. So there's a lot of potential to understand that information, to predict, for example, customer needs, and embed that in the development process. So that's a lot of work that we're doing at Northeastern to see if we can use AI to help improve that process. On the other side, there's platforms like Onshape are allowing the collection of data that allow users to understand how teams are performing things like creating new knowledge or revising that knowledge. And that can be used to improve the efficiency of the process, to see where at what stages the team is really producing new information. And for example, in Onshape, some of our research has discovered that it's really impacting the way teams ideate. So for example, in the very beginning of the process, you can have many people at the same time just cobble together what you would call throwaway prototypes and throwaway models. They're just really used to generate ideas. And that's one of the powers of having cloud-based technology.
Yeah, excellent insights, and it connects, I think, very nicely, I know, to some of the work, Jessica, that you're doing relating to prototyping and some of the challenges there. I'd love to hear you, first, if you have response to what Tucker shared, and then I have some follow-on questions as well, but I'll give you the chance to respond if you do have some thoughts there.
Yeah, I think I mean I agree, with Tucker's thoughts and processes, and I think that the really interesting aspect, especially if we take Onshape as a great example of a collaborative CAD platform, is that it is, allowing these softwares to be more like Slack, right, or Microsoft Teams, where I think that we've been kind of missing that in engineering, where Slack is largely used for software development and things like that, which is wonderful. But, these collaborative platforms like Onshape are really allowing engineers to work in a CAD-based environment much earlier on in the design process and rapidly change things around with the team. It's becoming a much more collaborative and open communicative process, as opposed to just one individual doing all the CAD, right? And having these people kind of work off in their silos and then come together at a later time and realizing issues later down the line. This collaborative platform kind of allows for earlier stage prototyping, getting people talking, getting people identifying the issues kind of earlier on, which ultimately saves money in the long run.
Yes, you touched on, the idea of getting them kind of talking, communicating earlier on. And I know, a lot of your work encompasses how these product development teams collaborate and how they communicate across different roles and functions. So when we think about, how informatics can help teams work more effectively, how do you see that happening throughout the various stages of the product design and development lifecycle?
Yeah, so I mean, I think broadly informatics, is really going to significantly improve the communicative abilities, right, of teams across the entirety of the product development process. I think when you look at things like collaborative platforms, digital design prototyping, even the advancements that have been made with virtual meetings and video conferencing, all of that is helping teams kind of work a little bit more efficiently, a little bit more effectively across the entirety of the scope. What I think where informatics is really going to be useful and coming into play is kind of what Tucker was mentioning, right? The ability to track everything, the ability to leverage big data to understand how teams are communicating, the frequency of interactions, the kind of back end of how they're changing CAD models around. All of that data can then be used to kind of start predicting team trajectories based on communicative signals, based on communicative patterns, right? So we can start leveraging the data that we are creating, because we're creating, hundreds of data, thousands, millions of data points each day with all of our interactions on these virtual platforms and collaborative tools. So if we can start leveraging that and pairing it with the communicative signals of team meetings, for example, to say, okay, this team meeting really went off the rails. Let's try and figure out what happened. And then looking at the different patterns and signals and drawing out the signal versus the noise, and trying to say, okay, well, when there is this pattern of interaction, we notice that the team kind of gets off the rails. Maybe it goes in a direction that's not useful. So all of this, I think, is building to kind of just-in-time interventions and real-time monitoring of team progress, of design progress, ultimately increasing speed to market, increasing speed to innovation. So that's kind of how I see informatics being used across the spectrum. But did you have a second part of that question?
No,
Okay.
that was great. Thank you. I know when when the four of us met last week, as it came up in the discussion, Jessica, I know you indicated, you sort of represent the human component of design, and John, you talked about being more the computational component, and Jessica, you talked about leveraging all this data, that we're creating all of this data all the time, and how can we use it to inform what we're doing. And so John, my question for you is, you really focus on developing new tools and methods to help engineers design better products, and specifically, in generative design. Can you share how generative design is different from generative AI, and how you think generative AI might be used for product development at some point?
Yeah, great question, Alyssa. And there's certainly been a lot of confusion in this last year or so, where generative has entered the mainstream consciousness as something of interest. And, in the sense of generative being an adjective, generative design is very similar to generative AI, in that both of them create new novel, I'll use novel in quotes, novel content based on a set of input. So broadly speaking, they're similar. In terms of the actual technical guts under the hood, though, the algorithms in play can be very different. So, for instance, generative AI is generally associated very strongly with machine learning algorithms, whereas generative design, at least as of today, actually has its roots, like most interesting things, has its roots in the 1980s and 1990s with topology optimization. But it's a very interesting point to make in the context of this discussion, because generative AI excels in areas where there is not sort of direct first principles equations that can easily be applied to a solution, whereas generative design has traditionally lived out of necessity, I'll say, in the area where there are first principle science, right? This is the FEA stuff, multivariate optimization. It's math, right? Applied mathematicians love it because everything makes sense from the beginning to end. But I really start to see the lines blurring here, and that's why I'm excited to be here participating in this discussion, because design doesn't exist in a vacuum. Maybe someday we'll get to the point where we can ask for a flying car and get it, but we're a ways away from that, and that means we really need to figure out how we interact around the product requirements, right? If you think about sort of the key data that goes into product design, it's really those product requirements. And you can separate the process of trying to arrive at the right product requirements, which Tucker mentioned is incredibly important and has huge implications on the entire life cycle of the product. I come more from, given a set of product requirements, how do you generate the optimal shape, or more abstractly, the optimal manufacturing instructions to best meet those requirements, especially when there are several requirements in conflict, right? Classic topology optimization, make it strong and make it light, right? Those are sort of mutually exclusive, you have to optimize. So generative AI in the short term, getting to excuse me, the second part of your question there, Alyssa. We're going to see a lot of interesting user interaction and requirement generation aspects, as both Tucker and Jessica alluded to. And Onshape is really the first platform where that's possible, because for those of you that don't come from a sort of CAD engineering background, CAD is traditionally a desktop software, and the vast majority of customers, rightly so, consider their CAD data to be highly proprietary and very secret. It's very difficult for researchers to get access to. Whereas Onshape, with the appropriate safeguards in place for information security, is able to be the first likely spot for meaningful data sets. And to be honest, in the technical world, we're still at the dawn of the creation of that data set. If you think about how much data goes into ChatGPT to make what we see today, 3D is both a more complicated domain, it's a higher dimensional domain than natural language. And there's also orders of magnitude less of it, which leads to lots of interesting research to be done.
Yeah. So I feel like lots to unpack and respond to there. Tucker, Jessica, I'd love to give you the opportunity to respond.
Yeah, I would just say, to John's point, I think it's something in my group we're actively looking at, right? You know, there's been these awesome challenges, like the GE bracket challenge is probably the most famous one, where there's these large digital design repositories. And we get so excited because it's, 700 or so designs that we have free access to and can download. But then when you think about it, right, I mean, ChatGPT was trained on the entirety of the internet, the entirety of it, right? So that's unimaginable to the human. Like, we can't, as humans, comprehend that magnitude. So I think, to John's point, we're very much in need of public databases to start understanding how to really leverage large data sets from a 3D perspective. And even if we think about maybe a closer caveat from natural language processing, image recognition and those kind of machine learning algorithms for images, when you take it to 3D, now you're working with something called like voxel based, right? So it's just, as John mentioned, it's incredibly, it complicates all of our algorithms and all of the ways we would approach these things. And I think that there's a huge potential there because, as John mentioned, and my earlier work was in topological optimization when I was just a small grad student. And so, that's kind of where we started, where we're looking at strength versus weight, right? That's the classic topological optimization problem. But now, as we start to kind of get to some of Tucker's work, some of my own work, right, as we start to consider the life cycle of these products, additive manufacturing, as an example, has kind of rapidly increased down the TRL levels, technology readiness levels, and it's producing designs through, topological optimization, through generative design that are wildly unique, multi-material, incredibly organic geometries, and it's wonderful, but then they cannot be inspected. So we've reached the limitations of our, for example, non-destructive evaluation techniques. And so this is problematic, right? So now we have to think of new optimization schemas that not only take into account the performance objectives, but also take into account, well, can we even feasibly inspect this part down the line? And if we can't inspect it, then we can't put it on an airplane, right? So, thinking into more holistically, how are we going to start integrating all of these constraints into some of this generative design, I think is kind of where we're starting to go and see some progress made. But yeah, I completely agree to John's points. It's incredibly complicated.
Just to reinforce what Jessica's saying, it's an additional requirement that we didn't really realize before. We don't talk about DFI, design for inspectability, so much in our undergrad engineering courses, at least when I went through undergrad.
Well, yeah, just to latch on to a couple comments here, is that when we think about generative AI, let's say look at DALL-E, right? If I type in, design me a weird skateboard, it will produce something. And that's great in the upfront of the process for ideation. Maybe it helps get a thought started. But when you start thinking about the requirements to design those flexible trucks on the bottom of a skateboard, now you're starting to get into what John is talking about, is real engineering issues that need to be grounded in first design principles, right? As he had mentioned. And the leap from one to the next, yes, we're making substantial progress, but it's very challenging. So I think all of us, involved in this space, be it from a CTO level or an academic research level, sees the potential, but there's a lot of holes that need to be filled in, a lot of work to get to that ultimate vision where we have. But you can see a platform like Onshape, with its ability to have APIs, things built on top of it, has the ability to be a conduit for that innovation. And I'll give a quick example. There are companies that are running their own feature scripts and developing their own APIs that can look under the hood at the usage data and to see where they can optimize or not optimize their process. So it's a huge opportunity for even us as academics to create some of these different applications that might lead to better generative AI or lead to process improvements with better understanding of the data.
Yeah, thanks, Tucker. And everyone, this is really interesting. Just thinking about some of the challenges, as you said, John, and I know Jessica, you alluded to this as well. Just when you go into the three-dimensional space, the new magnitude is even greater than, as you mentioned, the magnitude that we see now with just something like a Chat GPT. So Jonathan, I'll, as a sort of a follow-on question, we've talked a little bit about how, Onshape's cloud native platform is democratizing access to CAD, to modeling, simulation, and, someday generative design. So more data can be generalized and analyzed about how engineering tools are used to develop products. What are the biggest or the most important questions you think can be answered by analyzing these data?
Yeah, absolutely. And I think we've danced around a few of the important ones already. So as I think most are aware, Onshape added simulation inputs a few months ago, and some generative design capabilities were shown at PTC's user event a few months ago. So nothing official to say there, other than what Alyssa said, someday. But this is a hugely important piece of the requirements all being encoded in one accessible place in Onshape. Because before that, yes, Onshape had simulation plugins that weren't native, but researchers didn't necessarily have access to, at a very simple level at the FEA setup for load cases, for instance. So with that data alone, already with the magnitude of data sets that we have, I expect we'll be able to help users with their setup. And don't think Microsoft Clippy, oh, you forgot to constrain something. Yes, maybe that would be helpful. But what's really exciting to me is if you have generative design and enough data, you can begin to build models to approximate the inverse of generative design. So think about it as requirements discovery. And we've seen this all along with topology optimization, where somebody comes along, maybe they have a engineering analyst that knows some of the load cases, right? Some of these physical requirements that the part has to withstand. And so they plug those into the top end of generative design, and they get a design that meets those requirements, but it looks terrible. And they say, well, I can't use generative design because it produces bad results. Why is that? Well, there was probably some requirements that weren't encoded that were implicitly met just by engineers looking at the design that weren't encoded. So once we have enough data and can start to approximate inverse models, what's really exciting to me in the short term is being able to highlight, hey, look, you've got some extra material in your design right here, if that material is important, here's a load case that might exercise that material or, make that material required. So this inverse design is very interesting in terms of helping the users, right? The humans in the loop understand what they might be missing. And I'm sure Tucker and Jessica can both affirm that in the real world of engineering, very little design is done from first principles, and the vast majority is done iteratively. Given an existing design, change as little as possible to adapt it for its next use. And I'm really excited about the possibilities of generative in Onshape to help take the guesswork out of that and help people really understand what their designs are doing and why.
Right. And I might add, what's interesting, if you follow the history of computer-aided design, in the beginning, it replaced two-dimensional draftsman. When it went to 3D, the process didn't really change that much. Just our tool changed, and we're expressing the models in a three-dimensional way, ultimately leading to interesting work and additive prototyping and those sorts of things. But Onshape is somewhat has the potential to add real changes into how we collaborate and design. And in the 2000s, we did a lot of research to talk about, okay, if you can iterate 3D models very easily, that could lead to a condition of over iteration, right? So that's just the design team doing that. And that we call that condition backloading, right? So it's iterating later in the process, driving the process to actually miss scheduled deadlines. But with generative technology, the time and the human impact of massive amounts of iteration goes down dramatically. So you can have the ability to iterate and have great improvement without the impact on the design team, eliminating that condition to get backloading. So I think that's really fascinating about the potential of work that John has done and others, and where generative design is going, because it allows you to nearly instantaneously, yes, it will take time, but it's allowing massive improvements in efficiency or performance enhancements to the design much faster than you could before.
Yeah, this reminds me a little bit of some of, Jessica was perusing the thread group site and just looking at some of the work that's been done by your group there. And I know, one of the things that it talks about is just that prototyping and iterating can be risky, and that's something that your team there is looking at. And so one of the questions that I have is, how are focusing a little bit more on prototyping now, how are digital fabrication technologies and real-time collaborative design software changing the way that prototypes are used by product development teams? And what insights do you think could help teams use prototypes more effectively?
Yeah, for sure. I think historically prototyping and developing prototypes have represented one of the largest sunk costs for most product development teams. Typically it takes a lot of time, a lot of effort, and then what we don't really actually have good data on in the field is the value of that prototype. We can assign kind of a monetary value in terms of how much it costs in terms of people, time, and resources. But what we don't know, and the real aim of any prototype, is to learn about the product, right? And to understand the bounds and to understand where it's going to fail, identify problems, and then fix it very rapidly. We don't have a good way to assess that value, right? It's not something you can easily just assign a quantity to. And so I think that that's been a real challenge for the field. And what we're seeing with a lot of these digital technologies, particularly with additive manufacturing or collaborative cloud-based CAD systems, is that it's kind of enabling the teams to with a lot less time, more rapidly get to some sort of a tangible or 3D visualization of the product. And what that does is it allows teams, one of the main functions prototypes serve is as a communicative artifact, right? So helping the team communicate to external stakeholders, helping the team communicate internally, and really building a shared sense of understanding of the design. So we're seeing that as being really useful. The flip side of that is that it is now so easy to develop prototypes with like additive manufacturing that teams almost, what we've seen in some emerging research is that designers and design teams are actually becoming fixated on the like the prototyping technology to manufacture it. So they are unknowingly and kind of implicitly changing the design to meet the needs of the, let's say, additive manufacturing equipment. So, you know, all of a sudden they're putting in 45-degree overhead, right? They're changing fundamental features of the design to make it print faster, make it print easier, reduce support structure. And that's wonderful from an AM perspective. But when you lose sight of the connection to going back all the way back, the customer requirements, the product specifications, and now you're so far down the rabbit hole, we're seeing them come kind of out of that, realizing, oh, this is going to be manufactured in a large scale plastic injection molder, and they have to fundamentally redesign the product, right? So there is this interesting kind of fixation that's occurring as well with some of these technologies. I think ultimately, from my perspective, where these technologies are a huge benefit is not necessarily in tracking changes to the design, but monitoring and tracking changes to design processes, right? So looking at design decision-making and being able to have the capacity and the data sets to track every micro decision that is going on in a design process, and then ultimately correlating that with, you know, efficiency of the design process, effectiveness of the designers, ultimate performance of the final design, to try and understand when we can see these teams kind of, hey, you're getting fixated on AM, you're making changes that don't align with the product specifications, and kind of pull them back out of it. So that for me has kind of been the interesting part of all of these technologies.
Yeah, I know Tucker, and Jessica, I believe you both are connected with Alison Oliowski from University of Toronto and the Ready Lab there. John, I don't know if you're aware, but I know her lab is doing a lot of research around just the behavior of designers and design choices and the process, right, that the humans are involved in. Very interesting to hear some of those connections, and thinking about how the data can be used to gain greater insight into that and therefore improve the process, hopefully. So question, for the whole group now, and of course I'll remind our audience, if you have questions, please feel free to share those in the chat. We're coming down to the last 10 minutes or so of our discussion. But one of the questions that I have for all of you, and any and all of you can answer, is what sources or types of data are most exciting to you? And what do you also see as being the biggest challenges associated with them? And we've touched on some of this, but would be curious to hear what you see as being the most exciting.
Well, I'll just add a note just as a quick backup. Allison is actually the reason we started using Onshape and kind of studying Alyssa. So I can't speak highly enough of her. She's amazing. And really doing some cool work at University of Toronto. So go check her out if you're interested. But I think for us, and I've said it, I feel like a broken record, I've said it a million times now, what we are just absolutely loving and just blown away with, and particularly the Onshape software, is just the ability to see every single decision between CAD, right, in the CAD environment, to see every single decision that our designers are making, to track it, to, use Markov modeling to see larger level strategies. And then for us, what's interesting is we pair this with the communicative patterns exchange between designers. So either through Zoom or in real life, we're tracking all the things that they're saying, the verbal utterances. And we're interested in the future in tracking like physiological signals, behavioral signals, and kind of pairing all this together to understand how these are all related. Designer stress, for example, how that's all related to the actual technical outcomes, right? So I'm sure we've all been in a meeting where we've been frustrated and maybe things have not gone well, or you're hitting a wall in the CAD environment, and to have some sort of an understanding of how your own physiological stress might actually impact the technical design, I think could be pretty interesting from our perspective for the field. So that's one thing we're doing. And I'll take a second. If you're interested in that work, Debrina Roy is actually my grad student. She'll be presenting in the poster session following this, so you should check out her poster.
Great, appreciate the plug.
Correlate F-bomb usage to Onshape feature.
Yes, exactly. That's the goal.
Yeah, I do kind of want to jump on something that Jessica said a minute or so ago that I'm really excited about, which is the manufacturing aspect of it. So at Frustum, we've kind of seen three major parties in industry that oftentimes are in completely different departments, organizations, or even different companies that have to come together on a collaborative platform to get to the next level of design. And that's the actual modelers, right? The product designers, which is what Onshape was originally targeting. There's the analysts, or the people who are in charge of making sure the part doesn't break. But then there's also manufacturing, and Jessica did a great job explaining one of the many failure modes when the manufacturing process is divorced from the design process. And, you know, Onshape really holds the promise of being the first place where all of those data come together. And to Jessica's point, the interactions between those different parties are intriguing because, to be honest, oftentimes those people just chuck stuff over the wall. You know, design's done, chuck it over to manufacturing, onto the next. And we can all imagine the inefficiencies that brings, that Onshape holds major promise in being able to reduce or eliminate.
Thanks, John. Tucker, if you had any comments on.
Yeah, so just to follow on to that, and the first one, so I'm interested in data from two main perspectives, and one is following on with Jessica. You know, the ability to understand when a new part is created, when that is revised, and being able to get that click data that is provided on the back end enterprise capabilities of Onshape is so fascinating. To be able to understand that there could be changes of how teams are approaching the traditional divergent and convergent processes of design logic itself, and how that could move forward, and even changes in generation to generation, high school kids versus college versus older people, and maybe the way they use it is different. So it's really fascinating that we can have the ability to have a window into that. The second is what is exciting from our perspective in research at Northeastern is what can we do to extract user needs and wants, translating that into specifications and putting that directly into generative design. You know, having that connection for us is really important. We can do it with 2D now. We're hoping to do it with 3D. And of course, Onshape lends the ability with plugins to be able to see if we could prototype something that maybe that would lead to something that to be very interesting, to make that connection between massive amounts of customer data and the actual design of the part itself. So lots of potential.
Yeah, I do think it's interesting as the three of you have been talking, just thinking about, we have all this data, we're able to gain more and more insight into behaviors, into attitudes, into processes. And then, of course, you know, I think a natural follow-on question is, okay, once we have these learnings and findings, how do you convey that? How do you get teams to implement it in such a way that they do design more effectively, that they do collaborate more effectively? And, you know, I noticed there's a question in the chat. People don't always know how to do effective collaborative design. I often think of the analogy, I don't know if you've seen, there was a commercial a while back that showed, you know, a daughter was with her father in the kitchen. She asked him how he liked his new iPad. And he said, oh, it's great. And then she looks and sees him, he's just used it as a cutting board. He loves it. And, you know, there's a, you know, we've talked a little bit, I know in the education space where we're working in, you know, oftentimes in K-12 schools and also in some cases universities, that people are so used to doing things a certain way that even when presented with a new technology like Onshape that has so much capacity to and capability to improve the way they do things, that there's, you know, it's filling that understanding gap and recognition and getting them to sort of make that leap. So what would you recommend as a guide to teams, you know, as you're learning all of these things, how to be more effective in implementing some of the things that you're learning so that they can be more collaborative in their design?
So I think the easy answer is, well, we need to communicate with the user why things are the way they are. That mostly just rephrases the hard question in a different way. But one of the interesting challenges that we face with generative design, and it's true across many areas, is when you automate things, unless you get them right, darn close to 100% of the time, it can actually be more frustrating to the user to get something they didn't expect and not understand why, than it is to just do it the old way, step by step by step. And so certainly observability into the whys of anything automated, whether it's generative AI or generative ML. And of course, we're familiar with generative AI of many societal questions around the lack of, shall we say, transparency that large language models provide, at least the previous generation. So, that really goes back to one of the major challenges of informatics in general, and design is no exception.
Thanks, John.
Yeah, I'm gonna hop in. I think that explainable AI is going to be critical, right? Like making sure that people are aware, and we're seeing this in our own lab. I think, part of my answer to your question, Alyssa, is like, I'm hoping that humans don't have to do the management of collaborative processes, and that we can use AI to do the management of those processes. But with that, right? I mean, we're conducting studies in my lab looking at how an AI manages conversational dominance in a brainstorming session, right? Versus a trained design thinking facilitator. And to John's point, we had both the human and the AI operating with the exact same rules in terms of when to intervene. And because the human was a human and we didn't explain how the AI was working, all of the people on the AI teams thought our AI was broken. And it was typically the person who was dominating the conversation, because the way our experiment worked, we would only intervene to say, hey, we haven't heard from you in a while, would you like to speak? But we would not tell the dominant person, you're dominating this conversation. So these dominant individuals came back and said, it's broken, it never asked me to speak. I feel like I barely contributed to the conversation. Which is interesting, right? Because then we were able to show, well, actually, you were speaking for 90% of the 30-minute meeting. And so that's why you weren't pinged. And so I think a lot of it is just expectation setting, and comes back to expectancy value theory, right? And just making sure that people are aware of what's going on, and that we're being very transparent with how things are operating. But unfortunately, we are also in a mode where people expect things to work 100% of the time, 100% correctly, right? And so when AI, what was that?
And right now, right?
And right now. And so, AI, all of these things are going to take training, and it's a continual learning process. And making sure that we as humans understand that, I think, is a challenge.
And to add a comment to that, if you look at this burgeoning field, we like to call it multi-user design platforms. So you could argue Figma is one, Onshape is another, and from our perspective, in the academic term, there's things called affordances, which connect technology and actions and behaviors, and important, I think. Important critical characteristic for these MDPs or multi-user platforms is the fact that it allows for flexibility, right? So it allows, and we've seen this in even just using Google Docs, right? So there's a point in the process where we can just hack away at a paragraph or two. And then there's a point where maybe it makes sense for me to digest that information and work myself. And then Onshape can allow, if I do something, well, people can follow me, and it's transparent for what I did. So I still have that available to the team. So that's a good thing. But underpinning all of this is that for collaboration, there's some sort of coordination effort. There's affordances for iteration and revision. So there's multiple factors that can help a team actually use the inherent flexibility of the platform to its advantage. And I think that's what's really exciting about the capability of Onshape.
Thanks, Tucker. And John and Jessica, we are at time, maybe just a minute or two over. Thank you so much for such a rich discussion. I think we may have missed one or two questions in the chat. So If you want to take a minute and try to answer them there, I'll turn the time over to Paul, but thank you all again for the discussion today.
Thank you, Alyssa. Thank you, Paul, for having us.
Thanks, Alyssa. Thanks, everybody, for having me.